we're going to talk about seems like a stupid question. Is that big? How big is big, really? Last time we noted the sample average usually has a normal distribution. Asterisk next to the word usually. If you talk to mathematicians, you can rig up cases where that's not true. But a lot of cases it is. The sample average usually has a normal distribution. But we still have sampling variation. There's always going to be some differences from the true mean. But the question is that a big difference? How do we figure out how big is a big difference? How big does it have to be in order that we can call it big? Consider an example where we roll dice to see how many times comes up 6, and try to conclude if the dice are fair or if they're loaded to be unfair. We can represent this as a tree diagram. From the first roll, we can have 6 different outcomes of the dice, but keep the picture simple. Let's collapse that into concentrate on whether the dice comes out as 6 or some other number. That way, each level of the tree has just 2 branches. You roll the dice, either you get a 6 or you get not a 6. The next roll, you get either a 6 or not 6, and you keep doing that on and on. Now, I've shown you there the first 3 rolls in the table and highlighted the ones where you get 2 or 3 6 values. We can consider one candidate decision rule, testing the protocol to say, well, the dice is loaded if, when I roll it 3 times, 2 out of 3 times comes up 6, or 3 out of 3 times come up 6. You'd want to figure out what is the probability of each of those happening if the dice were fair. That is thinking like a statistician, which seems kind of like thinking upside down. It's a little bit weird because we say, well, what if there are actually no difference? What if there's nothing going on? What if the dice are not loaded? Actually, they're completely fair. Sometimes, even though they obviously look it in the experiment. But generally, we'd say there's a big difference if there's evidence that there's something really there. And a small difference is not going to be evidence that there's something there. And we'll come back to that again later. Failing to find evidence is not the same as evidence that there's nothing there. Absence of evidence is not evidence of absence. Those statements are a little bit different. But regardless, step 1 is measure if there's a big difference. And ask, well, how big is big? The law of large numbers makes the assertion that the sample mean is going to have a standard distribution, the mean mu, the true value, and the standard error is the standard deviation divided by the square root of n. Recall that previously we're looking at our sample of poles. If I went to 10, to 100, to 1,000, to 10,000 in the sample size, the variation got smaller. That's because we're dividing by the square root of n. The fact that it's 1 over the square root gives that diminishing returns. The formula for the standard deviation divides by square root of n minus 1, which might seem a little weird since I'm then dividing by square root of n minus 1 and then again by square root of n. But yes, that's actually what we want to be doing. We often standardize the test statistic by taking the estimate x bar, divide by its standard error, which is s over the square root of n, assuming the null hypothesis is that mu ought to be 0. The test statistic z would be expected to have a mean of 0 and a standard deviation of 1. The mean is unbiased, so as n gets larger and larger, then s divided by the square root of n is going to get smaller and smaller and smaller. So as n grows, we'd expect to get closer and closer to the true mean value. Now, where did this formula come from? It's actually pretty easy to derive just from our previous assertions about linear combinations. If z is x plus y, then mu z is going to be equal to mu y plus mu x. And the standard deviation of z is the standard deviation of x plus standard of y plus twice the covariance, all over the square root. And as we recall the other rules for linear combinations, for n equals 2, x bar is just half of x1 plus a half of x2. The mean is going to be half the mean of x1 plus half the mean of x2, but those are the same, so that's the mean of x. The expected value of the sample mean is going to be the true sample mean. Next, look at the standard error formula. The standard error of the mean is a half squared plus sigma squared x1 plus a half squared sigma squared x2 plus a bunch of terms of the covariance, but assume all the covariance terms drop out because covariance is 0. Take out the half, do a little simplification, find exactly our formula, 1 over root 2 times standard deviation of x. I'll leave for you to do the case of n equals 3 or n equals 4 or n equals any arbitrarily large number. The formula checks out.